Section 5.5, Zeros of Polynomial Functions. We begin with the theorem, the remainder theorem. If a polynomial f of x is divided by x minus k, that factor, then the remainder is the value f of k. So we want to use the remainder theorem to evaluate this function at x equals 2. Well, based on that fact, we want to find f of 2. That's it. Now, the remainder theorem says what we can do is divide by x minus 2. Okay, we can exchange this for x minus 2 equals 0 and use that factor. So we'll use 2. Write down our coefficients. We're going to go ahead and use synthetic division. So this will be 6 x to the 4th minus 1 x cubed minus 15 x squared plus 2x and minus 7 for our constants. So our remainder, which, if you recall, will be this term, this value, that'll tell us the value f of 2. So we'll bring down our 6. 2 times 6 is 12. Negative 1 plus 12 is 11. 2 times 11 is 22. Negative 15 plus 22 is 7. 2 times 7 is 14. 2 plus 14 is 16. 2 times 16 is 32. And negative 7 plus 32 is 25. That is my remainder. So f of 2 equals 25. And we could check that by actually evaluating that function at 2. Next thing we see is the factor theorem, which is going to relate the remainder theorem to some other things. If k is a 0 of f of x, not just the remainder, but if k is the 0, this is true if and only if x minus k is a factor. That is, if the remainder is 0. Okay. If the remainder is 0, then x minus k is a factor of that, which means that k is a 0. So we want to show that x plus 2 is a factor of this polynomial, x cubed minus 6x squared minus x plus 30. And we want to find the remaining factors. So let's first go ahead and divide this by x equals negative 2. And we can exchange those two. All right, so our coefficients are 1 minus 6 squared minus 1x and 30 for our constant. Bringing down 1, negative 1 times, or negative 2 times 1 is minus 2. Negative 6 plus negative 2 is negative 8. Negative 2 times negative 8 is positive 16. Negative 1 plus 16 is 15, and then minus 2 times 15 is minus 30, so that my remainder is 0. So that means the remainder is 0. So I can write x cubed minus 6x squared minus x plus 30. I can write that as x plus 2 times this polynomial, which is going to be x squared. So 1x squared minus 8x plus 15. Okay. That is based on my results of my synthetic division with a remainder of 0. Now I can factor x squared minus 8x plus 15. Let's bring down the x plus 2. That's going to be, let's see, 5 and 3. So x minus 3, x minus 5. Okay. And since that is now factor complete, those are all linear factors, my solutions, the zeros, are minus 2, positive 3, positive 5. All right, now this leads us to what is called the rational root theorem or the rational zero theorem, depending on your textbook. All right. This states that if we have a polynomial in this form, standard form, if it has integer coefficients, then every rational zero of f of x has the form of p divided by q, where p is a factor of the constant term and q is the factor of the leading coefficient. All right, so let's go ahead and make note that p, that is the constant term. So in this case, that is minus 4. And q is our leading coefficient, which is 2. So all of our rational solutions are going to be a factor of one of these. So negative 4, the factors are plus or minus 1, plus or minus 2, plus or minus 4. The factors of 2 are plus or minus 1, plus or minus 2. Which means the options are, we're going to take some combinations of these, okay, our possible solutions. Okay, and I should add rational on here. Possible rational solutions are plus or minus 1. Okay, so that is, I'm taking 1 divided by 1. Next I'm going to take 2 divided by 1, so plus or minus 2. Next we have plus or minus 4. I'm really just repeating that first list at this point because the first q is 1. Next I'm going to cycle through the second q here, so plus or minus 1/2. Plus or minus 1, we've already done that, and plus or minus 2 when I divide those two. So my possible solutions are on this list. Now if I want to know which ones of those are solutions, I need to evaluate the function at each of those, or I can use synthetic division as we saw a minute ago. Okay, so these things are going to tie together. All right, so the next question is going to combine what we just did, finding the possible solutions, with actually finding those solutions or those zeros. So use the rational zero theorem to find the rational zeros of this function. Based on the rational root theorem, our p is 1. Just go ahead and it is just 1, and our q is 2. So our possible solutions possible rational solutions form this list. We've got plus or minus 1/2, and 2 has a factor of 1 and 2, so we could also have plus or minus 1. So let me just write that out more plainly. All right, the factors of this one, plus or minus 1, factors of this one are plus or minus 1 or plus or minus 2. So dividing those, 1 divided by 1, there's our options there, and 1 divided by 2 is right there. So this helps us narrow down the choices. So what we'll do is go ahead and evaluate this function at each of those. Go ahead and evaluate the function at each of those and see what we get. If it's 0, then that's a 0, or a solution. So f of negative 1 is 4. So not that one. Positive 1 is 0. We found our first one. All right, minus 1/2 is 3. And positive 1/2 is minus 1/2. So the only rational zero we have, is 1. All right, example 5, find the zeros of this function. With any luck, one of these will actually have a remainder of 0 and be able to factor. All right, so our p is minus 1 and our q is 4. All right, so our factors are plus or minus 1, plus or minus 1, plus or minus 2, whoops, plus or minus 4. All right, so our possible solutions are plus or minus 1, plus or minus 1/2, and plus or minus 1/4. All right, from there, we could evaluate for all of these. Let's actually do some synthetic division. So let's start with 1. All right, so we'll take 4, 0x squared minus 3x minus 1. 4, so 1 times 4 is 4, 0 plus 4 is 4, 1 times 4 is still 4. Negative 3 plus 4 is 1, 1 times 1 is 1, and that is 0. All right, so this means that 1 is actually a solution. Okay, 1 is a solution, which means that I can write my equation, my original 4x cubed minus 3x minus 1, as x minus 1 times 4x squared plus 4x plus 1. Now, you can't in general just expect the first one to work, okay? So that doesn't always happen, but it does work. It did work here. Now, we could solve the second one. So we know one solution. We're trying to find all the zeros. One of the solutions is 1. We could solve the second by the quadratic formula, but I have a feeling that this factors. So let's go with x minus 1. Okay, and that is going to be, we're going to have a 2x there. Okay, plus 1 and plus 1. Could that work? 2x squared, that would be 2x and 2x, 4x plus 1. All right, so that is the complete factorization of this. So x equals 1. That's the one we found earlier with synthetic division. And then setting each of those equal to 0, well, they're the same. So 2x plus 1 equals 0. Tells me x is negative 1/2. Which was also on my list. So if I had evaluated, I would have found that value as well. All right. Next we have what is called the fundamental theorem of algebra. If f of x is a polynomial of degree n greater than 0, then f of x has at least one complex 0. So what this comes out to mean is that if we have a function, with a polynomial function with degree of n, it can be written as with n factors. C1, C2, C all the way to Cn. So if it's a third degree polynomial, we should have 3 solutions. Now, some of them may be complex, but we can have n solutions. So with a 5th degree polynomial, there are 5 solutions. Some may be complex, some real, but we're going to have a total of 5 in that case. So if we allow for multiplicities, okay, that's where I was talking about 0 actually representing 2 roots, or 2 representing 2 roots, something like that. Okay, if we allow for multiplicities, then there are n roots. It's the same as the degree. So example 6, this function is going to have 3 solutions. It will have 3 solutions. So let's first consider our rational roots, and if we can find one, we can then do synthetic division, and we can break things down a bit. All right, so our p is 3. Our q is also 3. The factors are plus or minus 1, plus or minus 3 for both of them, which means our possible solutions leads us to plus or minus 1, plus or minus 3, plus or minus 1/3, and I believe that is it. Plus or minus 1, plus or minus 3, plus or minus 1/3, and 1. Alright, so we have 6 possible solutions to try. And let's pick one. Actually, we may not even have to do that, because I believe this is going to factor by grouping. It will. Let's go ahead and factor that. So the first will be, you can factor a 3x squared, which leaves it with an x plus 1. No, x plus 3. Take out a 1 GCF, and this factors as x plus 3, 3x squared plus 1. And that is f of x. So it turns out that 3 actually was a solution over here, or negative 3 was. So let's set each of these equal to 0. The first is x equals negative 3. The second, 3x squared plus 1 equals 0, implies, let's go and put that down here, implies that 3x squared equals minus 1, or if we divide by 3, 3x squared equals, or just x squared, x squared equals minus 1/3, and taking the square root of both sides, that is going to be x equals I over root 3. We can't simplify the square root of 3. And we can actually use radical properties to say that's root 3 over 3i. Now, because we took the square root, this is plus or minus. Alright, so we have found our 3 solutions. Plus or minus root 3 over 3i and negative 3. Now, what we just observed shows why this next theorem is true, the complex conjugate theorem. It says that we are going to have factors in the form of x minus c, where c is a complex number. This theorem says that if a plus bi is a solution, then a minus bi is also a solution. That is, if we have a solution that is one that's complex, we actually have 2 that's complex, that are complex. So let's use this in example 7. All right, we have got, find the 4th degree polynomial with real coefficients that has zeros of negative 3, 2, and I, such that f of negative 2 equals 100. All right, well, we can write this as a factorization already, because we know the zeros. We don't know the leading coefficient, but this is based off of the fundamental theorem of algebra. F of x equals a times x minus c1 times x minus c2, etc. So x minus that, so we have x plus 3 is the first factor, x minus 2, x minus I, and based on the complex conjugate theorem there, we have x plus I. So that is it. It's a 4th degree polynomial, so we have 4 factors. Okay, 2 of those are the real solutions, and 2 of them are the imaginary. One's the conjugate, so plus or minus I are solutions there. All right, now let's see if we can find f of negative 2 equals 100 and use that equation to find out what a is. Now, I'm going to go ahead and multiply some of these things together. If we multiply the first 2 That'll be an x squared plus x minus 6. And if multiplying these two, that will be an x squared. The I terms cancel out, plus 1, because I times I is negative 1. Alright, so that will give us a times x to the 4th. Alright, and I've done a little bit of scratch work here ahead in advance here, so that's plus x cubed minus 5x squared plus x minus 6. Okay, and that is an alternate form of f of x. I prefer the factored form, but for now, f of negative 2 being 100 means the output is 100 if the input is negative 2. To the 4th plus negative 2 to the 3rd minus 5 times negative 2 squared plus negative 2 minus 6. Alright, so negative 2 to the 4th plus, well, okay, that's going to be 16 minus 8. Let's see, that's going to be minus, that's 4 times 5, so minus 20. Minus 2 minus 6. This is negative 20. So that makes negative 20a equals 100. And if we divide by negative 20, a must be negative 5. So our function f of x equals minus 5 times x plus 3 times x minus 2 times x plus I times x minus I. And that is the simplest form of that. Well, no, we could go ahead and multiply that out. And again, this is scratch work. But we could use this version of that. If a is negative 5, here, let's do that. If a is negative 5, then that would be negative 5x to the 4th minus 5x cubed plus 25x squared minus 5x plus 30. All right. So there is our polynomial. The next rule we have is Descartes' rule of signs, which gives us some bounds on positive and negative zeros. Okay, so it says that the number of positive real zeros is either equal to the number of sign changes of f of x or is less than the number of sign changes by an even integer. Okay, so we'll explore that with an example. And then the number of negative real zeros is either equal to the number of sign changes of f of negative x or is less than the number of sign changes by an even integer. For example 8, we will use Descartes' rule of signs to determine the possible numbers of positive and negative real zeros for f of x equals negative x to the 4th minus 3x cubed plus 6x squared minus 4x minus 12. All right, so we need to consider two things. First is the number of sign changes of the function itself, and then the second is the number of sign changes of f of negative x. So let's go ahead and write out what f of negative x is. That would be substituting as an input negative x. So negative x to the 4th minus 3 and negative x cubed plus 6 negative x squared minus 4 times negative x minus 12. Now, raising something to the 4th power will make this positive, so this is just minus x to the 4th. It doesn't change. The next, negative x cubed will introduce a negative, so this will be plus 3x cubed. All right. X squared will still be x squared. That'll be positive. plus 4x minus 12. Okay, now the number of sign changes for f of x means how many times it changes from the coefficients being negative to positive. So we've got negative to negative, nothing there. Negative to positive, that is one sign change. Positive to negative, there's another sign change. And then we have negative to negative, no changes there. So the number of possible positive zeros is either 2, scrap that, possible positive solutions is either 2 or it's less than 2, and it says that it differs by an even integer. So 2 or 0. It has to be less than that, going down by an even integer. All right, and now for a number of possible negative solutions. For negative solutions, we're just looking at sign changes in f of negative x. So we have negative to positive, positive to positive, positive to positive, positive to negative. So that means there are potentially 2 or 0. It's the same idea based on the number of sign changes. So we could have 2 possible positive solutions or 0, or we could have 2 negative solutions or 0. Now, interesting fact here is that it is an x to the 4th, so there have to be 4 solutions. Some of them may be complex. So we could have something like 2 positives, 2 negatives, and no complex. We could have no positive, 2 negative, and 2 complex. So we're going to have a combination of whatever's left over is going to be complex, but a combination of 0 and 2 for the positive and negative. Example, a bakery offers decorated sheet cakes for children's birthday parties and other special occasions. The bakery wants the volume of a small cake to be 351 cubic inches. The cake is in the shape of a rectangular solid. They want the length of the cake to be 4 inches longer than the width of the cake, and the height of the cake to be 1/3 of the width. What should the dimensions of the cake pan be? Alright, so we know that our width is W, and we want to write out our volume. So this is a rectangular solid. The length they want to be 4 inches longer than the width. So 4 inches longer than the width. The height they want to be 1/3 of the width. So we're going to have a 1/3 of the width for our height, and our width, we're going to use W. Alright, so I'm going to rewrite that so this is a little more clear. That is W times W plus 4. Actually, let's put the 1/3 W first. All right, and then W plus 4. So multiplying this out, that is going to be a W cubed, and actually it's a 1/3 W cubed. The first two is 1/3 W squared, distributing that, 1/3 W cubed, and then 1/3, or plus 4, 1/3 W squared. Now we know we want the volume to be 351 cubic inches. Right, so let's go ahead and rearrange this. Let's go ahead and solve that by subtracting And let's rewrite this because this just looks strange. That should be 4/3. The better way to write that. If we clear fractions, if we multiply everything by 3, then we get 1053 equals w cubed plus 4w squared. All right, so let's see. Rearranging that, w cubed minus or plus 4w squared minus 1053 equals 0. Now, the number of solutions, we might be able to use our Descartes' rule of signs to determine something there, or we could use our rational root theorem. Now, let's go ahead and do that. Our rational root theorem says that our solutions have to be factors of 100 or 1053, the numerators do, and the denominators have to divide 1. So 1053 has lots of factors, plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 13, plus or minus 27, 39, okay, 81 is a factor there, 117, 351 as we saw earlier, and 1053. Right, and our denominator is either plus or minus 1. So all we could really have is a positive solution. Okay, so all of the, we can ignore those minuses. Now let's go ahead and factor or plug in, evaluate into this function until one of those works. All right, so we've got v of 1, v of 3, v of 9, v of 13. Okay, I'm going to stop there in case one of those works. X cubed plus 4w squared minus 1053. Alright, evaluating that at 1 is negative 1048. We certainly want a volume that is positive. Negative 990. Or, it's actually not our volume, but that's the difference between the volume and our desired volume. So v of 9 is 0. Well, hey, that's great. Okay, so I could go ahead and do the rest of these, and I think I will go ahead. They're getting larger. Okay, bigger our x values, our inputs get for our width, the larger the volume is going to get. So the difference is going to be. So v of 9 equals 0. That means that our width is 9, which means our length is 4 inches longer. So that is 13. And our height is 1/3 of the width, so that is 3. So these dimensions are 9 inches, 13 inches, and 3 inches. And that brings us to the end of this section. Now, just like the last one, there's a lot of information here, so make sure that everything makes sense. It would be a good idea to write some of these rules along with the ones from the last section, just so that you have them all in one place when you need them, and find whichever